Welcome everyone to our video on the equilibrium law. In this video, we're going to first start out by defining the equilibrium law in words. Then we'll look at that expression mathematically. And finally, we'll do some equilibrium law expression practice for various chemical equations. Okay, so here's the equilibrium law in words. Give you a second to read this here. You might even want to pause the video. It's such a long definition. Got it? Make sense? Maybe not yet. It's quite a wordy definition, and there's a lot of confounding words here, and it's basically one run-on sentence here. So let's look at the mathematical equation because it's a lot easier, and then we'll explain it with the mathematical equation in front of us. Okay, we have a reversible reaction that can reach equilibrium. A and B on one side, C and D on the other. Their coefficients are the lowercase levels there. So that's the balanced chemical equation. When that system reaches equilibrium, the ratio of their concentrations, products over reactants, is equal to a constant. Okay? No matter what actual numerical values you have, the ratio of the products raised to those powers divided by the reactants raised to those powers is equal to a constant. We use the capital K value to represent the equilibrium constant. The equilibrium constant, K, is temperature dependent. We know that temperature affects the position of equilibrium. We saw that with Le Chatelier's principle. So the value of the equilibrium constant will change depending on what temperature the system's at. So we'll always have to reference temperature. We'll also treat this equilibrium constant as dimensionless, meaning that we're not going to worry about any units for the equilibrium constant, just a numerical value. Describing a situation where we can have a constant is important because we can apply that constant to various situations. For example, if we know the equilibrium constant K for a particular chemical reaction at a particular temperature, we can actually calculate equilibrium concentrations without having to measure them experimentally. You'll note that in all of the quantitative problems we've solved so far, we've always been given one equilibrium concentration. Well, if we know the value of K, we don't need that anymore. We don't have to be able to measure anything at equilibrium. The magnitude of K, how big or small it is, tells us about the position of equilibrium. Are the reactants favored, the left-hand side, or the products favored, the right-hand side? So this K value can also just tell us something about this chemical reaction at that particular temperature. Let's take a look at 4 examples here of how the equilibrium law constant can tell us something about what's going on in the reaction. Here we have a reaction, N2 and O2, synthesized to produce nitrogen monoxide, which can decompose and produce those reactants again. The equilibrium law constant is an incredibly small number at 25 degrees Celsius. At 2,100 degrees Celsius, it's a much larger number. Still small, but still a much larger number. Here we have the equilibrium law expression. Products divided by reactants. So when we have a K value that's incredibly small, that must mean the concentrations of the reactants, the left-hand side of the equation, are much larger than the concentration on the right-hand side. That would give us a number that is much less than 1. Now, this example here is an example of a harmful pollutant that's produced in internal combustion engines. So if we want to reduce the amount of nitrogen monoxide that's formed, we want to keep engine temperatures as low as possible. We see that when we have a very low temperature, around room temperature, 25 degrees Celsius, the chemical substances on the left-hand side are heavily favored. Here's another simple example, the decomposition of molecular hydrogen. Once again, at room temperature, we have a very, very small number for K. That number increases, a less small number, when we get up to very high temperature, 5,000 degrees Celsius. Well, the equilibrium law expression, products divided by reactants raised to their coefficients. If we have a very small number, that tells us that the left-hand side is favored. There's a very large number in the denominator compared with the numerator in that mathematical equation. This decomposition simply does not happen at low temperatures, and it only begins to happen spontaneously in any sort of regular amount at very, very high temperatures. The left-hand side of the equation is so heavily favored. In fact, this is a type of decomposition that, for all intensive purposes, we would label as like a no reaction because it simply does not happen under normal temperatures. Here we have the equilibrium that represents the decomposition of water. And going in the reverse direction, we have the synthesis of water. For the forward reaction here, the K value is another tiny, tiny number, 10 to the minus 41. Here's the equilibrium expression. Products divided by reactants. Right-hand side divided by left-hand side, raised to their coefficients. Well, if the K value is very small, once again, that must mean that H2O value on the denominator is much, much larger than the numerator concentrations. Well, this tells us that water vapor simply does not decompose at ordinary temperatures. Finally, let's look at an example with a large value for K. Here we have, going in the forward direction, a decomposition of acetic acid. Now, this decomposition is possible where acetic acid decomposes to form water and solid carbon. We don't see it very often. However, when we look at the K value, which is quite large at room temperature, we see that this product side is heavily favored. If we have a very large value for K, that means that the right-hand side is much more heavily favored. So looking at the value for K at 25 degrees Celsius, we'd expect this reaction to happen spontaneously at room temperature. But we simply don't see this happening. We don't see acetic acid just spontaneously decomposing to form solid carbon. And I use this as an example of one of the limitations of the equilibrium law expression. So according to the thermodynamics of this reaction should occur spontaneously. But it turns out that this reaction is incredibly slow. So even though it is technically happening, it's happening on a very, very long time scale. So we don't even see it happen, and we probably use that acetic acid in some other reaction before it even has a chance to decompose in this way. So the equilibrium law expression doesn't tell us anything about the kinetics of a chemical reaction, okay? That has to be treated separately. Let's switch over to the whiteboard and just do a few problems writing equilibrium law expressions. For the first example, let's determine the equilibrium law expression for the Haber process, which is the synthesis of ammonia from nitrogen and hydrogen gas. Our first step is to balance the chemical equation. Once the equation is balanced, we're going to write the equilibrium law expression. We'll use a capital K always. And then on the numerator, we have whatever's on the right-hand side, products. So the concentration of ammonia. And then it's written to the power of whatever coefficients in the balanced chemical equation, in this case 2. That's divided by the concentrations of the reactants, each raised to their coefficients from the balanced chemical equation. So here's the equilibrium expression for the synthesis of ammonia. Reminder once again that these concentration values are equilibrium concentration values. So this constant only exists, this relationship only holds when we're dealing with equilibrium concentrations. For our second example, let's look at the conversion of carbon monoxide to carbon dioxide. So once again, our first step is to balance the chemical equation. Now that it's balanced, let's write out the equilibrium equation. This would be a good time to pause the video and see if you can write that out now. Okay, so here is our equilibrium expression for this reaction. Now what I want to do for our last example is compare this equilibrium expression to this same reaction but written in reverse. Okay, so we have the same equilibrium system, the same chemicals on each side, but I've just written it in reverse. So let's write out the equilibrium expression for this reaction in blue. So here is my equilibrium expression for the reverse reaction. If we compare the equilibrium law expression for the forward reaction and that of the reverse reaction, we can see one is just the reciprocal of the other. So for any chemical system here, the equilibrium law expression for the forward reaction is going to be equal to 1 over the equilibrium expression for the reverse reaction. This will become useful because sometimes we will be given an equilibrium law constant for a reaction in a certain direction, but we will be solving a problem looking at the reverse reaction. So even though we're not going to be given a specific K value, if we know the K value for the reverse reaction, we can just do 1 over that value and get the K value that we need for the reaction that we are interested in. So this right here is a very important relationship to understand and know.